Ladies and gentlemen, good afternoon. We are going to start with chapter 9 today in the textbook of Cengel and Ghajar. We've already done chapters 4 on transient heat conduction, chapter 6 on fundamentals of convection, chapter 7 on external forced convection, chapter 8 on internal forced convection, and now the last part is natural convection, which we're going to finish this week in 3 lectures, and then next week we're going to do the part on the heat exchangers, which is the most important part, bringing everything together. So chapter 9 is on natural convection, and it starts with the physical mechanism of what natural convection is. Now, examples where we get natural convection and where it is important is where you're sitting at the moment. Where you're sitting, you're releasing heat, and that heat actually goes up, and the velocity of that convection stream is very, very low. You almost can't measure it. Other examples are the cooling of your cell phones, the cooling of refrigerators, cables, lots of electrical equipment. In many venues, steam radiators are being used to heat venues, not really so much in South Africa, but more overseas in cold climates. Power transmission lines, bodies of animals, and food and drink. An example, an egg which has been boiled. If you take an egg that has been boiled, it is very hot, and you put it on a surface, what is going to happen is this air is at a lower temperature than that of the egg. So what happens is that the air next to the egg will be heated, its density decreases, and the result of that would be that it moves upward in that direction. And if you do that everywhere, you'll get a convection stream doing something like that. Okay, now that would be for gravity in that direction. If you would take an egg that has been in a refrigerator and which is at a colder temperature than that of the outside air, maybe the outside air is 30, then this convection stream will be in the other direction. Another example is a soft drink, a Coke or Tab or something like that, which is cold on a hot day. Again, the air will be cooled there, and it will start moving downstream in that direction. Okay. Here the flow is much more complicated. I'm not going to draw it even there. Well, if it has been heated, maybe it was in a car and it stayed there for a few hours and the car was out in the sun, then this can be easily at a temperature of 50 degrees Celsius. If you now put it in a cold environment, then the airstream will now be in a different direction. So depending on if you have heating or cooling. Now in an environment where there's no G, like in space, there cannot be any natural convection. Okay, so if G is equal to 0, there can be no natural convection. Even if you've got a spacecraft and it's full of air and it goes up into space, the moment where the gravity starts being negligible, then there cannot be any natural convection. So the physical mechanism is, I've mentioned here with the air, that the hot air rises. That is not actually technically correct. This comes from the fact that if we have a body, let's suppose a ship, and there it is in water, it displaces a certain amount of water, and the ship has a weight of W, then the net force would be equal to W minus the buoyancy force. The buoyancy force, the weight would be equal to the rho of the ship, the G and the volume of the ship, minus the rho of the fluid, the volume of the ship, and G, which we can write as the difference in density multiplied by the volume multiplied by G. So we can see the difference in density is very important. Now this is actually what happens here. It's a difference in density. But in heat transfer we would like to work with temperature. So we actually would like to write this as a function of temperature. And this is being done with the so-called volume expansion coefficient. The volume expansion coefficient. The volume expansion coefficient is equal to beta, and it is equal to 1 divided by the specific volume multiplied by the partial dV dt at the constant pressure. Now 1 divided by the specific volume is the density. So here we have actually density multiplied by the partial derivative to temperature of 1 divided by the density. We are not going, now this you can write as a function of density, as I've mentioned, and then you can go through all the calculations and then actually show that the difference in density is equal to rho multiplied by beta minus T infinite. So this is important because it shows that the difference in density is because of the difference in temperature. Okay. So the temperature difference causes a density difference, and it is actually the density difference causes the buoyancy forces. Now, that is now some of the things I wanted to show you on the PowerPoint that I can't do today. But experimentally, lots of experiments are being done on natural convection problems. They are very difficult because the temperature differences in many cases are small and the velocities around the body are very small, so they are very difficult to measure. Now, if you make use of an interferometer, then you can take photographs, and the photographs shows you maybe for, if this is a flat plate, it will show lines like that. And these lines are actually because of the diffraction of light, and these diffraction of lights can be photographed, and these lines represents the flow streams over a body. So by doing that, you can actually see if the flow is laminar, and in some cases, of course, if the flow is turbulent, you'll see lines like that, much more complicated, and you'll see some examples of that in your textbook. So, getting to the equation of motion, paragraph 9.2. Equations of motion. The simplest geometry for us to consider in heat transfer is always a flat plate. And this is also where the studies of natural convection started, looking at a flat plate and then consider that as the x direction and that as the y direction. And from these studies, they have found that typically there will also be a boundary layer that forms because of the flow over this flat plate. So that temperature has been considered as Ts. And then, what is now different here, well, let's first start with the temperature. So with the temperatures, if you go and take temperature measurements, you'll get temperature measurements something like that, if Ts is larger than that of the environment. So the temperatures will look like that. Remember, temperature is not a vector. I'm just using that distance to indicate the value of the temperature. So the temperature at the wall would be at its highest, and then it would become less and less until this temperature is the same as the temperature of the environment. That would be the end of the boundary layer thickness, the thermal boundary layer thickness. Now, if we look at the velocity profile, then it's the same as that of the flow, the convective flow over a flat plate, except for one difference. Here, the velocity would be equal to 0 because of the friction. Then it will increase, but then it would become 0 again. If you move far away from this flat plate, then the convection streams, the changes in density here, will cause us flow disturbances, but far away nothing will happen. It wouldn't know that. So the velocity distribution is going to look like something like that. Okay, now in this case, I've showed the velocity distribution going in the upper direction, that is U and that is T. However, if this temperature was smaller than that, then the velocity distribution would be in that direction, and the boundary layer will start developing from the top and getting thicker to the bottom. Okay. Now previously, we've looked at a small block inside that boundary layer, and we have used the boundary layer equations to look at the sum of the forces, and we have also considered the continuity equation, the momentum equation, and the energy equation. And here we're going to do exactly the same. All the details are in your textbook. And these are then being solved, firstly, after this has been non-dimensionalized, can be solved using the boundary conditions. Now the boundary conditions are the same except for this one, where previously that velocity was equal to the free stream velocity. That velocity is now equal to 0. And the result of that is an x momentum equation that looks like this, u multiplied by partial du dx. I'm not going to put in all the terms, but one of the terms that now starts looking different is the term that appears that looks like this. See, GB multiplied by temperature difference. And this is not, you have to non-dimensionalize it, and then this is going to change a little bit. But the result of that is that a new non-dimensionalized variable now appears, which is called the Grashof number. And the Grashof number is equal to G multiplied by beta. Beta is this volume expansion coefficient, which tells us the change in density, what would the resulting changes be in terms of temperature. G beta multiplied by Ts minus T infinite multiplied by the characteristic length to the third divided by the kinematic viscosity squared. So that is called the Grashof number. And the Grashof number represents the ratio of buoyancy forces to a viscous force. Reynolds is momentum divided by viscosity. This one now is the ratio of the buoyancy force divided by the viscous force. Now, in problems where we have natural convection, if you now think in terms of what you've done in the previous examples and in the previous chapters, we have learned that the Nusselt number is a function of the Reynolds number and the Prandtl number, and I've previously mentioned to you actually the Grashof number also, but in the previous chapters we have ignored this part. Now here the Grashof number starts appearing. What is important now is if you go and look at the values that we typically have for these non-dimensionalized values, then this value is now going to start having very high values, magnitudes, 10 to the 6th, 10 to the 9th, while the Reynolds number is going to be almost negligible, because the Reynolds number is directly related to velocity. And I've mentioned to you that the velocity with natural convection is very, very small. If you just think of cigarette smoke, the velocity at which it goes up, in the order of magnitude of 0.1 meters per second, which therefore means that the Reynolds number is actually negligible where we have natural convection problems. Now that poses a new challenge to us, because now the problem is, well, how do we determine if the flow is laminar or turbulent? It is still important also in for natural convection problems. And the answer is we now use the Grashof number. So the Grashof number indicates to us if the flow is laminar or turbulent. Now, typically for a vertical plate, Grashof of 10 to the 9 is considered where transition will occur. 10 to the 9. So if it's smaller than 10 to the 9, the flow would be considered as laminar. If it is higher than that, it would be considered as turbulent. Now, unfortunately, and that is now what is now very unfortunate with the PowerPoint, is there are also some more detail in the equations here which we don't have time to write down now. But in these equations, specifically in that one also, we are going to have actually a Grashof divided by Reynolds square. That ratio is going to appear in the equations in your textbook. Now that is a very important ratio, because it tells us if a problem is being dominated as a forced convection problem or a natural convection problem, or a combination of the two. So let's look, for example, at a case where we've got a cylinder or a sphere. It is being heated, so it is hot, and the flow around it would do something like that. Then the flow would be a natural convection problem. There is no fan and there is no pump. Nothing forcing the flow over the cylinder. Now for these cases, the ratio of the Grashof number to the Reynolds number is larger than 1, much larger than 1. So that would be for natural convection problems. For a forced convection problem, if that is the cylinder or the sphere, and you put a fan here, and you force the flow around the cylinder, then it is forced convection. And for forced convection problems, the Grashof number divided by the Reynolds number square is much smaller than 1. And then the third category of problem is now where you actually have the sphere, and what do you see here? A very small fan. Okay, so a very small one. Because now the flow is going to be considered where there's lots of natural convection. However, the flow patterns or streams would do something like that. Okay, and this is considered as a mixed convection problem or a combined convection. Let's rather say combined. Combined. And for these cases, the Grashof number divided by the Reynolds number squared is approximately the order of magnitude of 1. Okay. Now coming back to the Grashof number. With the Grashof number, there are usually two challenges for students. If I go and look at all over the years and all the exams, where did students make mistakes in this? Or when I've given them a heat transfer problem where there's natural convection and they have to solve it. There are two places where students normally make mistakes. The first one is getting the value of beta. The expansion, the volume expansion coefficient. And there are two reasons for that. The first one is the values are given in your tables at the back of the textbook. Okay? So that is where you're going to have to go and get the values. Now in your textbook it is also mentioned that beta is approximately equal to 1 divided by the temperature in Kelvin. However, this is only for an ideal gas. Now air is a good example of a fluid that can be considered as an ideal gas problem. Water, no. If it is a liquid, it cannot be considered as an ideal gas, or if it is busy with condensation or evaporation. If it is a superheated steam, then you can consider it as an ideal gas. And then you can actually get the value of beta from this equation. So take note, you cannot always calculate beta from this. Always first try to get it from your tables. If you cannot get it from your tables, then you can only get it if you make the assumption of ideal gas. So this is the first mistake that most students will make. If I look at statistically at where are all the mistakes that students make. Okay, now the second one is LC, getting the characteristic length. Getting the value of the characteristic length is always in the fine print of the textbook. It's in the fine print. Okay, so those are the two things that you have to be careful for. Now specifically in this chapter, now I think many of you have learned that you have to check the fine print. And with many of the tables, they would typically tell you that. And this also happens here, but in this chapter it is even more important to look at the table, but also to read the text. Okay, also read the text with it. And specifically, the text that goes with table 9.1. There are texts associated with table 9.1. It's short paragraphs, but they tell you exactly how those equations should be used and when you can use them. So you have to be very careful for that. Now in general, you have learned that Nusselt number can be written as a constant multiplied by Reynolds and Prandtl number. Like that. And that was typically for forced convection problems. Forced convection. Now that we've got natural convection, now the Nusselt number can be written as a constant and in most cases multiplied by the Grashof number multiplied by the Prandtl number to the n. Okay. And because we have these two together so many times, the Grashof number multiplied by the Prandtl number, it is called the Rayleigh number. Okay, so it can be written as a constant multiplied by the Rayleigh number to the n to the n. Okay, now with the L, of course, I'm trying to indicate this is based on the characteristic length. So this is called the Rayleigh number. Now usually, in most cases, C is less than 1. It will have a value less than 1. And N would typically be a quarter for laminar flow and approximately a third for turbulent flow. Now it is specifically what I wanted to show to you on the board is table 9.1. So table 9.1. So here I want to say, read the text. And I'm not referring to the text here in the table, I'm referring to the text next to it that actually refers to every one of these problems one by one. The table 9.1 is on page 540, and the first one is the vertical plate. Now on page 541, there's a paragraph for vertical plate. Do you see it? It actually already started the page before that, and it addresses it in terms of vertical plate, a constant wall temperature, and the vertical plate, a constant heat flux. Then vertical cylinders, inclined plates, etc. Every one of that is very important. So please do not use the table without looking at the text. So in the table, they would, for example, show you a vertical plate like that. That is in the first column. In the second column, they tell you what is the characteristic length that you should use. And in this case, it is very easy. It is that distance there, distance L. And then they give you the range of the Rayleigh number. From where to where is it valid? So for example, for the vertical plate, it is valid from 10 to the 4 to 10 to the 9th. And the next one was 10 to the 10 to 10 to the 13. Take note, there's a misprint there in the textbook. So I trust all of you have corrected it in the table. Okay, I've given it to you in the study guide. So if you don't have the correction here, you're going to make an error in the exam. Okay, and then, so that's for first equation, and then there's a second equation, and then there's the next one is an entire range, and then you'll see a longer equation there as equation 921. So there are equations 919, 920, and 921. And students now always ask me, well, which one of these should I use? This one is for the entire range. That one is for a smaller part of the range. However, what is the difference? The difference between that equation is it's much simpler. It's going to take much less time in the exam to calculate. Okay, so if I'm you, and if you're lazy as I am, you can choose the simplest one, that's fine. Except if I explicitly tell you accuracy is very important. Then you will have to look at the more complicated equation, which hopefully would be more accurate. Okay. So the first case is that of a vertical plate. The second case is that of an inclined plate. Now it looks very simple. Most of you will not look at it more than once. You'll say, oh yeah, I'm sure I can do that in the test and exam. Until I give you the problem and you really start reading this, and then you realize, but wait a minute, it's more complicated than I thought. For example, it says for the inclined plate, use the vertical plate equations for the upper surface of a cold plate and the lower surface of a hot plate. and replace G by G cos theta. So for example, just as an example, this equation 919 is Nusselt number is equal to 0.59 Rayleigh to the fourth. Okay. So the Rayleigh number is the Grashof number multiplied by the Prandtl number. The Grashof number you have to calculate like that, and they tell you the characteristic length is the length of the plate. So it's very easy to go and calculate it. To calculate firstly the Grashof number, then the Rayleigh number, put it in here, you can get the Nusselt number. So in here they say you must replace G by G cos theta, where theta is that angle. And again you will say to me, oh, but that's very simple. Until I give you a problem in the test and exam. And then suddenly you're going to discover that suddenly I do not understand when I can use this equation and when not. I will come back to it just now. The next category of problem is that of a horizontal plate. Okay, so now the plate is like that. Okay. And again there are three equations, and they specify, they say for example horizontal plate, the surface area A and the perimeter P. So what they now here say is that for this one you calculate the characteristic length by the surface area, no wait a minute, AS divided by P, sorry. AS divided by P. So AS is the surface of the plate and P is the perimeter. You see, they explicitly tell you how to do it. But that's not enough. You still need to go and read the text together with it. So, and then they say it is for the upper surface of a hot plate or the lower surface of a cold plate. That's the case of A, and then there are two equations that you can use. And then the last case is B is the lower surface of a hot plate or the upper surface of a cold plate. So now it becomes a little bit confusing. What is the reason for that? Well, the reason for that is that these equations here typically work for the cases where if that is the plate like that, then the boundary layer starts forming as we've shown there in the derivation. Something like that or something like that. However, you get situations where typically if that is the plate like that, and this is now a hot plate, larger than that, then the flow would do something like that. It would break away and it will form plumes with a natural convection then doing something like that. So it goes up and then plumes are being formed. And you also would get it for a cold plate. The cold plate at the bottom, where typically the plumes would do something like that. And you will see that these two cases are not covered in the tables. It's the more complicated cases. That equations you can get in literature, but they're not available in the textbook. The other category of problem that is difficult for students when they first experience it is the case of the constant heat flux. Okay. Now why is this case now more difficult? Because with a constant heat flux, if you've got a surface and there's a constant heat flux, remember then the temperature increase is going to do something like that. Okay. Now if you go and read these tables and the text, it would actually tells you that all the properties should be at the film temperature, which is half of that of the surface and the free stream. So all the properties at the film temperature. Okay. Now if I give you a problem of a flat plate and I tell you the flat plate is being heated at a heat flux of 3 kilowatts per square meter, go and calculate the temperatures or whatever. then you don't have any temperatures to work with. You'll only have that temperature. So, again in the fine print of the textbook, of your textbook, it will tell you that you need to define that as the temperature at half length, at L divided by 2. And you need to do iteration. You cannot solve this problem the first round about. So you have to assume a temperature, put it in all the equations, and iterate it until it converges, normally very quickly. Right, I think in terms of theory, I've covered all the theory that I want to cover, paragraphs 9.1 to 9.2. There's paragraph still 9.4, which is natural convection from thin surfaces and printed circuit boards. And I think I'm going to finish it quickly. I'm going to make it. So paragraph 9.4 shows us a class of problem where typically we have fins. Okay. Now, you should have seen lots of equipment that have lots of these fins, typically on one or other surface. Okay. Again, natural convection applications. Now, what is now different with these fins is that if you compare it with this, you will also see it's a natural convection problem. However, now this boundary layer will grow, and that boundary layer will also grow. And at the stage they're going to meet. From there on, the heat transfer coefficient would obviously be fully developed. So you're actually trying to avoid that these two boundary layers meet, or the optimum is typically very close to the point where the two boundary layers meet. So in these types of problems, what is now very important is we will have a Rayleigh S or a Grashof S. So it would be equal to GB Ts minus T infinite, and the characteristic length would now be equal to S. And S is the spacing between the fins. Okay. Divided by viscosity square, like that. Okay. So now this thing starts becoming very important, and people like Avi Bar-Cohen at Maryland and Professor Grashof at MIT, they originally worked on it, and you'll see that typically they give you their information on what should the optimum value be of S. So equations are given for that. And furthermore, through that paragraph, more information for different applications. And from that, you can always try to determine the optimum spacing between these fins. Things which starts becoming very important is the thickness of the fin. So here, so typically the thickness T of this fin, and it can also start playing a role in all the equations, all the refinements on specifically the purpose of what they've tried to do in terms of optimizing fins for electronic, normally for electronic components, and what do you call these things that you, transformers. Okay. Okay, ladies and gentlemen, I think I've completed most of the theory for this chapter, most of the most important theory. With the next two lectures, we will do some problems. Thank you very much.